morning. We continue with the subject on dissociation of gases. Let me put the problem in a slightly different context. What do we mean by dissociation of gases? Supposing you have H2O steam being formed in the products of combustion at high temperature, this will probably, maybe if the temperature is quite high, change into something like H plus OH, because this fellow cannot be stable at that high temperature. Therefore, if I burn hydrogen and oxygen and expect the combustion temperature to be large, maybe I will really not get H2O as a gas or steam, but rather I may get H plus OH and some more of H2O. And now the question is, how do I estimate this? When we did the simple calculation, we looked at stoichiometry. When we looked at stoichiometry, we said the completely oxidized products of combustion H2 plus half O2 is being formed. Like we had C plus O2 is equal to CO2, which was again completely oxidized products of combustion. But if the temperature or the heat release in this reaction is very high, then perhaps I may still end up with H, I may end up with O, I may end up with OH and maybe other dissociated species. Similarly, if carbon and oxygen, mind you, the composition could be different, could still be, we say, a stoichiometric composition, but at high temperature it causes the species to be more dissociated. Instead of having a final or a completely oxidized species, we get species which are dissociated species. Therefore, how do you find the proportion of these things is the question which we like to ask. And we were talking about this, we said, well, we will do something like an equilibrium of the products which are formed, maybe the products, maybe the reactants together, and see under what condition we can get this. And this is what we were trying to do. For this, we introduced the word Gibbs free function, Gibbs free energy. And what did we find out? We found that dG, that is the change in Gibbs free energy, was equal to VdP minus SdT. And we also asked ourselves some question. Supposing I have a system in which not only does PdV work, but I do some work on the system and this work was d zeta, then I got the equation as the change in Gibbs free energy is equal to VdP minus SdT plus the incremental or the non-PDV type of work. And it is this non-PDV type of work what we are looking at. We want to make sure that there is no net changes taking place, that means no net further changes are taking place. I want to find out under equilibrium conditions what is the type of species what I get, and that is what I want to solve. Namely, we are therefore said if d zeta, that is the non-PDV work, is 0 and we are looking at dG at, let us say, constant pressure, a constant temperature, and then what happens to me? This knocks out, dP is 0 at constant pressure, dt is 0 at constant temperature. I am left with the that is the non-PDV type of work. And since no work is getting done on the system, well, for equilibrium we say Gibbs free energy at constant temperature and pressure is equal to 0. I think this must be clear to each one of us. The Gibbs free energy tells us when the system is in equilibrium, and what do we mean by equilibrium? No further changes are going to take place, and we say the change in Gibbs free energy is 0 when there is no further changes are possible. And when no further changes are possible, when the composition of all these things remain invariant as it is. I think it will become clear. Let me take one more example. Let me take the example because the concept is a little more involved. Let us say I have a tank containing hydrogen, let us say hydrogen gas. Let us say it is at room temperature of 25 degrees centigrade, which is equal to 298 Kelvin. Now I heat this gas to something like, let us say, 2000 degrees. At 25 degrees centigrade only hydrogen gas is there. Let us say the pressure of this gas is equal to 1 atmosphere. I heat this gas to a very high temperature, maybe allow maybe the top here to be a freely floating massless piston instead of a container, such that the pressure is always 1 atmosphere here. I heat the gases to something like, let us say, 2000 degrees centigrade. Mind you, the pressure I maintain constant because this is a massless piston, the ambient pressure is 1 atmosphere, the pressure here is still 1 atmosphere. And now at 2000 degrees centigrade, perhaps some of the hydrogen may change into H plus H, maybe part of the hydrogen may change. Supposing I heat it to something still higher, let us say I heat it to 4000 degrees centigrade, then maybe I may get more of this because I know I can dissociate hydrogen, I get more hydrogen. Therefore, now I ask myself a question, at 1 atmosphere and 298 Kelvin, the equilibrium is all hydrogen. At 2000 degrees centigrade, maybe I get a little bit of H and H atoms and more of A and some part of hydrogen, or rather if I were to look at the partial pressure of the gas, maybe pH2 at 25 degrees centigrade is 1 atmosphere and the partial pressure of hydrogen atom is equal to 0 because everything is hydrogen molecule. Maybe at 4000 degrees centigrade, we will work out this problem today. What is going to happen? Maybe the pH2 plus pH is still 1 atmosphere and therefore it could be something like 0.4 atmospheres and this could be 0.6 atmospheres. Therefore, what is it happening? I am getting more and more moles of the dissociated species at high temperature, and mind you, in a rocket chamber the temperatures are quite high, and instead of getting species like CO2, H2O and all that, I may start getting species which are broken into fragments like OH, H and stuff like that, and therefore I may not be able to get the entire energy to be liberated here. But there is something else which is extremely important that concerns the flow in the nozzle, which I will come back a little later. Is this clear and why we are doing this problem? If this is clear, let us go back to this definition. We said dG is equal to 0 at constant temperature and pressure for a single medium, for a single species. Now I tell myself this particular one dG I wrote as dG is equal to VdP minus SdT, and I am considering this, maybe let me forget about the equilibrium part, maybe some non-PDV type of work being done. I ask myself, supposing I have dG coming from a variation in pressure VdP minus a variation in temperature SdT, and now instead of having, let us say here I saw a single component gas, a single component, I put a constituent, let us say a gas A and a gas B in it. There are two gases. I want to know, to define dG, what is going to happen, what is the number of moles of A, what is the number of moles of B. I tell myself Pa plus partial pressure of species A plus partial pressure of species B is equal to the total pressure in this particular system, which is P. Now as I heat the gases, I expect some increase in A and B depending on their equilibrium. I have still not defined equilibrium, mind you, and therefore now I say when I have a two component gas, the moment I put more of A, what I am going to do, I am going to change the value of dG by the number of moles of A I am putting, but number of moles I am putting is keeping B constant. I put DNA moles, and therefore the change in Gibbs free energy when I add DNA moles of A keeping B constant, I can write it this way, and similarly I put some moles of B in this, I can write is equal to dG plus dNB keeping A constant into dNB over here. In other words, for a multiple component system like I have A and B, therefore I say in addition to changes in pressure and temperature which causes a change in the Gibbs free energy, now I also write plus dG by dNA keeping, now I keep these two also constant, pressure, temperature has to be kept constant, plus all the component B has a constant into dNA, plus I have dG by dNB keeping pressure and temperature constant and keeping now A constant into dNB. This particular term comes because now I have a multiple species system, whereas this part of the equation which we had derived in the last class was for a single component system. Now I keep on adding, supposing I say I have n components of the gas, then the equation slightly becomes a little more clumsy, but mind you, it is still the same. You say dg is equal to, you have vdp minus sdt plus what is it we are talking of? Let us put it in a general form. We have dg by dn, let us say j, into dni. Let us say what is it we are going to maintain constant? We are going p to be constant, t to be constant, and we are going to make sure that j is not equal to I. That means j is not equal to I, all other things are held constant except the jth constant. When I say dn1, this must be dn1, when it is 2 it must be 2, only that is changed, and therefore I can write it in this form, and now I add all of them together. I make sure that I goes from 1 to n in a multiple component system where you have species maybe A, B, C and all that, to maybe F or something. We have this is n1, n2 moles, n3 moles and so on up to nn moles. I have just increased the two things to multiple things. Let us keep it a little general. And what is this value of dg by dnj known as? You add per mole of I added, the change in Gibbs free energy is spoken of as chemical potential I. What chemical potential tells us, when I add 1 mole of a particular substance, keeping all the moles same, no change in pressure, no change in temperature, that is what we call as chemical potential mu. If this part is clear, I can go forward and we can readily find out how to calculate the species what we are talking of. I can now write my equation dg is equal to vdp minus sdt plus summation of mu I into dni. Okay? Now I want to simplify it further. At constant temperature and pressure, dg at constant pressure, constant temperature, I write this as equal to summation, let us say I is equal to 1 to how many species are there? I write it as maybe I is equal to 1 to n of mu I into dni, or rather I can write Gibbs free energy at pressure and temperature is equal to mu I into ni. Summation is over all i's. Chemical potential into the number of moles is giving me this at constant pressure and temperature. We will make use of this, we will define it, and we will make use of this to be able to formulate what are the number of moles which of hydrogen and hydrogen molecule and hydrogen dissociated hydrogen atom which are formed over here, and extend it to any possibility. Let us do that. For that I will go back once again to the basic equation what we have here. For a single species, I have to relate it to partial pressure, and that is where my problem is, and that is what I am trying to do. We have dg is equal to vdp minus sdt. Supposing I were to say dg by, let us say I from dt, and why did I do this? I am interested in finding out the composition of a gas at a particular temperature. Therefore, at a particular temperature I am looking at the value of dg by dp at constant temperature, and if I do this, well, the temperature is constant, this gets knocked out, and therefore I get dg by dp is equal to v. Is it all right? I think we will be clear. But from ideal gas equation we know PV is equal to the number of moles into universal gas constant into T. Let us be very clear, PV is equal to m RT specific gas constant, N into universal gas constant R naught into T, and therefore I can write this particular equation as equal to dg by dp at temperature is equal to, I now say V is equal to N R0 into by P, dG is V n R0 T by P. And now if I were to integrate this equation at constant temperature, that means I again integrate at constant temperature for a pressure change from a value, say a reference value P reference, to a partial pressure P, we get the Gibbs free energy G as equal to n R0 T ln P going from P reference to the pressure P. The standard reference of P value of P reference is taken as 1 atmosphere generally, and assuming this value, assuming the value of G corresponding to the reference pressure as G naught, we can now write the value at any partial pressure P as equal to G is equal to the value of G naught over here, or rather I get G is equal to G naught plus n R0 T ln P. We must remember that this G naught, I should have put the reference value, that is the 0 as a suffix rather than as a suffix. This is how it is done. The standard value at G naught is given in textbooks at the temperature T and at P at the reference value of pressure. Having said that, now I look at this form of the equation, and what should be the unit of G? G has units of H minus Ts or U plus PV minus Ts, that means it has units of energy. Therefore, G has units of kilojoules. Maybe I learned to do it in terms of G by N is equal to G0 by N plus R0 T ln of P. Therefore, I call this now as my G, this I call as G naught plus R naught T ln P, where the unit of the Gibbs free energy which I am going to use henceforth will be so much kilojoules per mole. Okay? I would rather have a per mole rather than for the total, and this whole thing is for n moles, therefore per mole is what I get over here. Now let me take a look at this equation, and let me take a look at this particular equation, which is Gibbs free energy is equal to mu I. Therefore, here also I find G so much kilojoule per mole at constant pressure and temperature is equal to mu I. Therefore, I can also write, based on this equality, I can write mu chemical potential is equal to mu 0 plus R naught T ln of P, ln of I get ith constituent partial pressure over here Pi, and this is the equation for the chemical potential. Okay. Therefore, what is it? Let us put down whatever we have done so far, such that we can draw on these things a little later. We have written that mu I is equal to mu I at standard plus R naught T into ln of Pi. Just in the same way, G is equal to G naught plus R naught T into ln P. Well, this is for a single constituent. Here I have extended to a multiple, wherein I have I, and for the ith constituent I am writing it. Now, I want us to get a little more of physical understanding. Let us go back to this problem of, let us say, I have a gas, let us say maybe a constituent, let us say hydrogen, a constituent H over here. I heat the hydrogen gas at constant pressure, as it were. That means I have a massless pistons surrounding here, ambient pressure is 1 atmosphere. Since it is massless and frictionless, the pressure here is 1 atmosphere. I heat it. I tell myself, when I heat a gas, I write this equation H2 becoming H plus H at a high temperature. But at high temperature, H plus H is also going to combine to give me hydrogen. Therefore, I should be able to really write this equation as H2 in the forward direction it goes in this, in the reverse direction it comes as H plus H. What is my aim? To find out how much of H and how much of H2 is there in this particular gas, right. This is what I want to do. How do I do this? Now I say let the reaction rate constant for this forward reaction, that is the kinetic rate constant for hydrogen being converted to H and H, I call as small kf, and all of us when we studied combustion we say we use the law of mass action, and what does the law of mass action do? The law of mass action says that the rate of a reaction, let us say the rate at which the active concentration of H2 changes with time goes as a constant into the value of the species itself, that is the rate of a reaction is proportional to the active concentration over here. That means I say dH2 by dt, it keeps depleting, I have minus kf into H2 over here. I want to write the same equation for this reverse one. I say yes, forward reaction is kf, backward reaction is kb. I can write the rate at which dH changes with respect to dt goes as kb into, I have 2 of this H into H over here, and mind you according to this reaction this also keeps decreasing. Therefore, now I tell myself that means the reaction proceeds in this particular direction, the reaction of H plus H proceeds in this direction. Therefore, the rate at which hydrogen gets depleted is proportional to the hydrogen, and the rate at which the H atoms get depleted because of the reverse reaction is in this, and therefore, for equilibrium the rate of these things must be the same, and therefore, I can write Kf of H2 is equal to Kb of H into H, or rather I can write now K forward divided by the backward reaction is equal to H square divided by H2, and what is H and H2? The concentration, or we say the law of Max says it must be the active concentration, but in any reaction we normally take it to be the total concentration of the substance. And for a particular reaction, instead of writing concentration, I can also write it in terms of partial pressure of hydrogen squared divided by the partial pressure of the hydrogen, because the concentration of hydrogen of H atom is going to be proportional to the concentration over here, because it is a given volume, and in a given volume at a given temperature we say how is partial pressure defined. Let us put that down again. We tell ourselves from the ideal gas equation PV is equal to N moles into RT, concentration is defined as N over V, which is equal to N over V is equal to P by RT, and for a given pressure and temperature for a given temperature concentration goes as pressure. Okay. Therefore, we find concentration, and for a real gas you all would have studied about fugacity, which is the real pressure of a non-ideal gas, maybe fugacity of hydrogen square divided by fugacity of hydrogen. But let us not forget into fugacities and concentrations, let us just look at a partial pressure, and we were interested in finding out when we have hydrogen and hydrogen atom at 1 atmosphere pressure, what is the partial pressure of the hydrogen molecule, what is the partial pressure of the hydrogen atom. This is what we wanted to solve. Now we tell ourselves, well, the forward reaction divided by backward reaction goes as this, and this particular term is what is termed as equilibrium constant. Known as K equilibrium. Therefore, having defined this, let us write out what is the expression. For the particular case of H2 going to 2H, I can say that the equilibrium constant of the reaction, which I say is K suffix equilibrium, is equal to pH squared divided by pH2. This is a definition of equilibrium constant. Any reaction you say under equilibrium conditions it goes as pH squared by pH2, or rather if I have a set of gases maybe A, B, C, D, E which is reacting, and supposing I have A molecules of A, I have B molecules of B, I have small c molecules of C, I have small c molecules of D, I have small e molecules of E and all that, and these things comes from a reactant. Let us say I have a reaction in which, let us say some reactant R1 with R1 is reacting with R2 with this is reacting to give me all this. The equilibrium constant of this particular reaction I can now write as equal to, I have PA1 partial pressure of A1 to the power A, partial pressure of partial pressure of A to the power A moles, partial pressure of B to the power B, similarly partial pressure to the power C and so on, divided by partial pressure of reactant R1 to power R1, partial pressure of reactant R2 to the power R2. In other words, for simplicity I can write it as product, that is product of, let us say the products Pi to the power Ni divided by the product of the reaction, maybe this is for the products, for the reactants I have Pi to the power Ni. A smaller way of writing, which is the equilibrium constant of a particular reaction. Now I just want to spend another 2 minutes on what decides this. See, we have still not analyzed our problem, and what was the problem we were considering as an example? We were considering the problem of, let us say, hydrogen enclosed in a particular volume at constant pressure, that means a freely floating piston. I wanted to find out what is the concentration of H and H2 at a given temperature, maybe at a given high temperature, and let us go back to this problem. But before that, maybe I need the, if I know the value, let us write it out. What did we get for this particular H and H2? Let us write out, we had K equilibrium is equal to P H squared divided by PH2. What do we find from this? If the equilibrium constant is a large number, then dissociated species will be higher. If the equilibrium constant is a small number, very small number, then the denominator will be a large number. That means I tell myself, well, equilibrium constant gives me immediately a view of whether H2 will be more or H will be more. But how do I calculate it? I want to calculate the value of pH2 and the value of pH. This is what I want to do. But I know I can use K equilibrium and do that. Therefore, let us find out how I get the value of K equilibrium. Therefore, what is it we have defined so far? Let us quickly revise what we have done such that we can build upon it. We told ourselves K equilibrium is equal to, maybe we are looking at maybe the partial pressure of products to the power of the moles divided by, maybe for the products, let us say, partial pressure of reactants to the power of the moles of the reactant. This is all what we are saying, and this is the product, this is the product over here. Now I want to get the value of K equilibrium. Let us take this simple example. Let us take the example of a species A going to a species B. See, I am very particular that we must have different ways of doing it. I keep telling in terms of reactants R1, R2, maybe products, so that we can immediately guess or be able to do any problem. Let us consider as a reaction in which hydrogen H2 as A, H as B over here. Now what is happening? The value of K equilibrium I want to find out for this reaction, but before that I have a problem. I tell myself, look here, in this reaction DNA moles of A gets consumed, that means it is getting consumed, and what is happening is DNB moles of B is getting formed. But since it is a 1:1, the number of moles here is 1, the number of moles here is 1, therefore I should also get DNA, which is minus, is equal to DNB, which I say is d chi, because the magnitude has to be same, because this is 1, maybe if I remove something that must get manifested here, therefore it is equal to d chi here. Therefore let us write the value for this particular reaction. Let's take back and put the value in terms of the chemical potential over here. Now what is the value of the summation of mu over here? Mu is equal to the mu for the species A and B put together is going to be, DNA is getting formed, therefore I can write it as mu I dot plus R naught T into ln of Pa. Okay, this is the value of mu for this, and what is going to happen? It is going to get converted, or the value of chemical potential of B is going to be plus I get, I will come back to filling this gap. But when I look at the change in the number of mu, maybe what has happened is the changes which are taking place in the chemical potential corresponds to minus DNA, or which I say I can now write DNA as equal to d chi and dNB as equal to plus d chi, because minus sign over here, and therefore I get something like, I have the value of minus d chi here and the value as d chi here, that is the net change in chemical potential which is taking place, or rather this should have been the change in chemical potential or the change in the Gibbs free energy. Or let us just keep quiet, we will just say, well, the mu I can write it in this particular form, and therefore, but I tell myself that this is the value of the change in d mu, let us keep it d mu, which is same as the change in Gibbs free energy dg. I will again repeat, since I made some summary changes over here. I get mu is equal to mu I, the change in mu is equal to this into the number of moles of change, the change in Gibbs free energy for the product B is this into the dNB which has changed, the change in mu is essentially the change in Gibbs free energy, because we saw this and this were equivalent, and therefore I can write that dg is equal to this. For equilibrium, I have dg is equal to 0, and what is the value? Even if we are not bothered about this one, we still have maybe mu a plus r naught t into ln Pa, we have this, and therefore I get mu a minus mu a plus mu b plus r naught t into ln of Pb by Pa is equal to 0, or rather now I get the value of the product divided by Pa into ln of this is equal to, this becomes my change in the Gibbs free energy. Mind you, this is standard, therefore it is equal to a standard here, and now I bring R naught over here. This is kilojoule per mole, this is again kilojoule per mole Kelvin into Kelvin kilojoule per mole, and this Pb by Pa is the partial pressure of products divided by partial pressure of reactants, and this is equal to ln of K equilibrium is equal to delta G 0 by R naught into T. But there must be something more to it. You know, I get the change here, I get this over here, therefore mu b minus mu a, therefore it must be something like minus delta G by RT is what is the value of ln K equilibrium. Or let us keep in mind, I am relating the change in K equilibrium to the change in the standard Gibbs free energy over here. Let us try to understand it through a problem and then come back to this. Let us go back to this problem we were wanting to do. If we take any book on combustion, the values of standard Gibbs free energy at a given temperature is given. I will take the values of this from one of the books which you all use very often. The book is by Turns, SR Turns, and the name of the book is Introduction to Combustion. All combustion texts give the value of delta G for the different substances, and I think this book, the second edition or the new edition, came out in 2006, and we have a large number of copies in the different labs, therefore it is easily accessible. If we are going to look at temperature, I will just take two values. I take the value of at let us say 300 Kelvin, and I take the value at let us say 4000 Kelvin. The value of G naught, that is the standard Gibbs free energy, at 300 is given in terms of kilojoule per mole is equal to 203 for hydrogen atom. For H2 it is 0, and at this again G0 kilojoule per mole. At 4000 the value is minus 15.3 kilojoule per mole, and it is again 0. Therefore, now if I were to find out the equilibrium constant for the reaction, let us say H2 going to H plus H, then I am going to take the value of delta G, that is delta G, let's put it together on this part of the board. Ln K equilibrium at let us say 300 Kelvin is equal to minus delta G naught by R naught T, and this gives me the value as equal to 203 into joules 8.314 into something like 300, that is the change for the reaction H2 to H, this is the value. And whereas if I were to write the value of ln K equilibrium at 4000 Kelvin, it is the same thing is going to give me the value minus over here, and the value becomes plus. We said 15.3, that is 15,300 divided by 8.314 into 4000. Therefore, now what is it we observe? We observe that the value at 300 ln K equilibrium is a large negative quantity, and K equilibrium is therefore a very small number, and therefore what we get is more of hydrogen will be available, and the proportion of hydrogen I can always calculate, because I know the value of K equilibrium from this equation. This is equal to pH squared divided by pH2. I can find out the proportion of pH to pH2 from this. At the higher value of 4000, I get the value as 15,300 divided by this, which is a positive number. In other words, a large positive value of equilibrium constant tells me that the proportion of the products is much higher. Let us do one or two small examples and still get this notion little more clarified. See, actually ln K equilibrium will never be positive or negative. When I say ln K equilibrium is negative, all what we are saying is K equilibrium is a small number. When we say ln K equilibrium is a positive sign, then K equilibrium becomes a larger number, even though that means when I say a negative quantity, K equilibrium becomes a very small number, and therefore pH2 is larger. When I say K equilibrium is a positive number, well, the value of K equilibrium, the ln K equilibrium is a positive number, well, the products are larger. But why is it we are considering all this? It is not only, before I go back and show some results, we must remember that in any combustion chamber, the temperature of the products of combustion is quite large, and therefore I can get dissociated species over here. What do we mean by dissociated? I get CO, I get CO2, I get maybe something like O over here, I get maybe carbon in the solid phase over here which is dissociated, I get H, I get OH and all that over here. Now let us go to the next step. This dissociated gas I know how to calculate, we will do it through an example. And now I expand these dissociated gases in a nozzle. What happens? I expand the gases, let us say again I have the dissociated species expanding in a nozzle, and what happens in a nozzle? As the expansion takes place, the temperature keeps falling because it is expansion, therefore the density falls, the temperature falls, the speed or velocity increases. Now here the temperature is very high, therefore I get all these dissociated species. As I move downstream of the nozzle, what is going to happen? The temperature falls. If the temperature falls, maybe the dissociated species are going to combine to form the species again. That means if I were to plot the heat release during nozzle flow, what is going to happen is as temperature falls, the amount of dissociated species get decreased, and for equilibrium to take place, what is going to happen? I am going to get more complicated things like H may not be there, I will start getting H2 again, which is more full, and the heat gets released, and therefore maybe the heat release will take place in the nozzle itself. In other words, as the flow takes place in a nozzle, I get equilibrium which is shifting at each point. At this point I get all dissociated, here I get the equilibrium which is not that much dissociated, here I get equilibrium which is still not dissociated. In other words, what is it I get? I get a shift in equilibrium as the flow takes place in a nozzle, right. But if the shift in equilibrium takes place, what is going to happen? I am going to get some heat energy, and therefore such type of cases wherein I have equilibrium taking place in a nozzle or a chemical equilibrium is known as shifting equilibrium. As compared to what did we consider earlier? We just took the properties at the entry to the nozzle, and what were the properties we took? We took Tc, we took the molecular mass of the products, we took the gamma of the products, and we worked out what is the jet velocity. But in practice with shifting equilibrium, what is going to happen? I get more heat release, molecular mass is going to change, and therefore my Vj must be higher, and therefore compared to frozen which we considered earlier, that means we considered frozen flow in the nozzle, now we are talking of shifting equilibrium flow in a nozzle, I will get more heat release, and therefore my ISP will go up. I think I have to consider this in further detail with some figures to you, but therefore a nozzle flow is not that simple after all. If I have chemical reactions taking place, because the equilibrium is changing at each particular point, I get heat release taking place at each particular point, and therefore recombination takes place, giving me a net higher value of the specific impulse. We will keep this in mind. Let us do a problem. In fact, I will come back to all this before I complete the portion on chemical propellants, but let us just go back and say, supposing I am interested in a products of a reaction, like let us say I have the reaction of hydrogen and 1 mole of hydrogen with A1 moles of oxygen, and let us say it gives me B1 moles of water at a high temperature, plus part of the water is dissociated into OH, part is dissociated into H, part is dissociated into oxygen. Let us say the temperature is going to be quite high, I want to determine the temperature, and to be able to determine the temperature I need to determine the value of B1, B2, B3 and B4. I also need the value of A1. How do I get the value of A1? We told ourselves in rockets we define fuel to, or we define a term known as mixture ratio, and what was mixture ratio? Yes, mass of oxidizer to mass of fuel, and if we take this particular one wherein I have A1 moles of oxygen, I have 32 of A1, that is the mass of oxygen, hydrogen is 2 which is equal to 16 A1, and mixture ratio is specified. It could be stoichiometric will be 8, if it is fuel rich that is where we want to operate our engine. It could be 4, it could be 5. Let us say I choose a value of 5. Therefore, I get A1 is equal to 5 by 16. That means in any rocket we must be told what is the mass of oxidizer to the mass of fuel, and accordingly I choose the value of A1. Therefore, A1 is known, and what is it you have to find out? You have to find out in the products what are the moles of B1, B2, B3 and B4. Therefore, we would like to find out for a given value of A1. Therefore, immediately I say, hey, this problem is quite simple. I know I have H2, I have O2, therefore, I have the atom balance equations. I have 2 of hydrogen, 2 of H, and therefore, I have 2 B1 plus B2 here plus B3. I also have 2 A1 over here of oxygen, 2 of O atoms, and therefore, I have B1 plus B2 plus B4 over here. I have these 2 equations which represent the atom balance equations. But now, I need to determine the value of B1, B2, B3 and B4. That means, I need 4 quantities, I have only 2 equations. Therefore, I need 2 more equations to be able to determine this value, right. Therefore, what are the equations I rely on? I say that the products are in equilibrium, that means the net thing is in equilibrium. Therefore, I do equilibrium analysis or a chemical equilibrium analysis, and from chemical equilibrium I say, well, I can think in terms of water dissociating to OH and H, or I can think of hydrogen dissociating into 2H, I can think of oxygen dissociating into 2O, or I can get H2 plus half O2 to give me water again. Therefore, I use these 4 equations, and for each of these equations I write Kp1 is equal to POH into pH divided by pH2O, or rather I can write the value of pH in terms of Kp1 into pH2O divided by POH. If I consider the reaction H2 going to 2H, I have the equilibrium constant Kp2 as equal to pH squared by pH2. If I consider O2 going to 2O, Kp3 the equilibrium constant coming as PO squared, because I have 2O here, that is PO squared divided by PO2, and if I consider hydrogen and oxygen giving me steam over here, H2O as gas, I get Kp equilibrium for this reaction as equal to pH2O divided by pH2 and PO2 to the power half. That means, I use the value of these 3 equations and I solve for the value of PO, and I get from this equation I get PO2 is equal to under root Kp4 divided into under root pH2 divided by under root pH2O, and again I substitute the value of maybe pH2 from here, and I get the value of PO as equal to pH2O into Kp2, Kp3 half, Kp4 and pH square. In other words, using these 3 equations I am able to get the value of pH in terms of pH2 and POH. I am able to get the PO in terms of pH2O and pH squared, and pH I already know in terms of POH. Therefore, instead of having 4 constituents, I reduce the value into 2 constituents, namely the value of maybe pH2 and POH. Maybe you all should try it out. You need not necessarily take these equations, but any system of equations. All what we are doing is we are trying to find out the partial pressure of hydrogen in terms of water and OH, and similarly partial pressure of oxygen in terms of H2O and OH again, because pH I already know in terms of this. But then what is it we get here? We get the value of partial pressure of hydrogen, partial pressure of oxygen, but what I really want is the number of moles B1, B2, B3 and B4. How do I convert it to moles? To convert partial pressure to moles, I need to know the total number of moles, or rather let us do it on the board. If the total number of moles is, let us say, NT, and the number of moles of H2O is H2O, then I say the number of moles of H2O into the total pressure is equal to the partial pressure of hydrogen. All what we are saying is the molar ratio, the total number of moles is NT, the moles of H2O is NH2O, therefore, pH2O depends on the total pressure into the fraction of the molar concentration over here, and that is what I do in the next one. Therefore, to convert you need to know the total number of moles, but we do not know the value of B1, B2, B3 and B4. But how do I get it? Well, let us assume a stoichiometric combustion. For stoichiometric combustion means we say the products of combustion formed are complete, that means I have H2OG, and to get H2OG I now get, if I have H2 plus A1 oxygen is equal to H2OG plus I have balance of oxygen, therefore, it gives me the total number of moles as equal to A1 plus half. And then I convert this into partial pressure of the products, namely I should be able to get B1, B2, B3 and B4, and maybe I will continue this in the next class. I will just get started at this point in time. We will see how to get the number of moles of B1, B2, B3, B4, and this will be an iterative process because we are assuming something, we have to correct for it, and this is what I will continue with in the next class. Well, thank you then.